the floor where they drop like bombs. Faceless voices running all the cons. Digital whispers in a binary night. No light, no face, pure sound, no sight. Stories unfold in the dark, unscrolled. Echoes of silence, secrets untold. Waves crash loud in this audio cave. No mic, no fame, just the sound we crave. Tune and turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just a vibe that's real. Faceless words you can touch and feel. In shadows, voices untamed. No need for spotlight, no claim to fame. Just a beat of life in a stream of thought. Every word a punchline, no need to be taught. Just listen close, no visuals needed. Raw conversation, unprocessed, unseated. Feel the pulse in every sentence said. No distractions, just thoughts in your head. Whispers of the streets, rumbling through. Faceless yet vivid, a world in view. No mic, just souls, connecting in flow. Pure and raw, let the rhythm go.
Thank you for the warm introduction. It is a great honor to be here. I must say, I'm rather surprised to find myself in this particular context, but I'm always ready for an interesting conversation. Well, a computable language is a language that can be processed by a computer, more specifically a Turing machine. A Turing machine is an abstract device that consists of a tape, head, and a set of instructions. The machine can read and write symbols on the tape, which can represent any information. The machine can also move the head in any direction, allowing it to process the information on the tape. In essence, a computable language is a language that can be processed by a Turing machine. A Turing machine can model a formal grammar by using the tape to represent the symbols of the language, and the states to represent the production rules of the grammar. The machine can read the symbols on the tape and follow the production rules to determine the next symbol to be written, or move the head accordingly. This allows the machine to generate all the possible sentences or words in the language according to the grammar. In a way, the Turing machine acts as an interpreter of the grammar, generating all the valid sentences or words possible. The universal Turing machine can simulate any algorithm by first encoding the instructions of the algorithm into a series of symbols on the tape, and then using its states and transitions to follow the encoded instructions and perform the necessary steps of the algorithm. The machine can move the head around the tape to read and write symbols, representing the memory and data necessary for the algorithm to be executed. By simulating the algorithm in this way, the universal Turing machine can carry out any computable task that can be expressed as an algorithm. The Chomsky hierarchy is not directly applicable to the universal Turing machine, as the Chomsky hierarchy is a categorization of formal grammars and languages, whereas the universal Turing machine is a theoretical model for computing. However, the universal Turing machine can be used to represent regular languages, type 3 in the Chomsky hierarchy, by being programmed to follow the regular grammar rules. It can also be used to represent context-free languages, type 2 in the Chomsky hierarchy, by being programmed to follow context-free grammar rules. The decidability of natural language parsing is limited by the inherent ambiguity and complexity of language. Natural language is often filled with idioms, slang, double meanings, and sarcasm, which can make it difficult to accurately interpret. Additionally, the complexity of human language is vast, with thousands of words and infinite combinations of words, making it virtually impossible to capture and accurately parse all possible permutations of natural language. For these reasons, natural language parsing remains a challenging problem in the field of computer science and linguistics. There are several limitations that can affect the computability of a Turing machine. One limitation is that the tape of a Turing machine is usually considered to be infinite, but in practice, it is not possible to build a machine with an infinitely long tape. Another limitation is that the number of states in a Turing machine is finite, which can limit the complexity of the computations it can perform. Additionally, there are also practical limitations on the speed and size of the machine that can result in practical limitations on its computable capabilities. Banburismus is a method of cryptanalysis developed by Alan Turing and his team during World War II to break the German Enigma machine, which was used for encrypted military transmission. Linguistic entropy, on the other hand, is a measure of the unpredictability or randomness of a language. In the context of Banburismus, linguistic entropy was used as a statistical measure to help identify patterns in the encrypted messages. By analyzing the statistical distribution of characters in the ciphertext, Turing and his team were able to identify clues and make educated guesses about the possible plaintext messages and ultimately break the Enigma code. In my 1936 paper, I provided an answer to the halting problem, which is a famous problem in computer science that asks whether it is possible to determine for any given finite input whether a given program will run forever or eventually halt. In the paper, I proved that there is no general algorithm that can solve the halting problem for all programs. In other words, there is no general method to determine whether a program will halt or not, as there will always be some programs for which this cannot be decided. This is a fundamental limitation of computability and algorithm design. The generative power of 1936 computability framework is unlimited. This means that it can be used to represent or compute any computable function or relation. In other words, if a function or relation can be computed at all, then it can be represented by a Turing machine. This is a powerful and fundamental property of the framework, as it allows it to serve as a basis for the theory of computability, and to model the behavior of any computation that can be carried out in a finite number of steps. In my 1936 computability framework, the decidability boundary refers to the boundary between problems that are decidable and those that are not decidable. Decidable problems are those that can be solved by an algorithm or procedure that always produces a correct answer, while non-decidable problems are those for which there is no such algorithm or procedure. For example, the halting problem, which asks if a given program will run forever or eventually halt, is an example of a non-decidable problem, as there is no general algorithm that can solve it for all programs. My Entscheidungsproblem proof relies on the axiomatic foundations of mathematics, specifically set theory, logic, and the theory of ordinal numbers. In particular, I used the following axioms. 1. The Peano axioms, which establish the fundamental properties of the natural numbers and arithmetic operations. 2. The axioms of first-order logic, which define the symbolic language and rules of inference for logical reasoning. 3. The axiom of choice, which states that given a collection of non-empty sets, there is a choice function that picks an element from each set. To optimize the search for the rotor settings in the BOM, my team used a method called crib dragging. This involved finding a short sequence of characters, known as a crib, in a partially deciphered plaintext message that was known to be in the original plaintext. Once we found a crib, we used it to narrow down the search for the rotor settings by focusing only on those settings that produced a similar sequence of characters in the deciphered ciphertext. This significantly reduced the number of potential rotor settings that needed to be tried, making the search more efficient and effective. In our efforts to decrypt the enigma, my team relied on a variety of statistical methods to analyze the patterns in the intercepted ciphertexts. We used frequency analysis to identify patterns in the distribution of letters and groups of letters in the ciphertext. We also used tabular analysis to create tables of letter and group frequencies, which helped us identify common letter combinations and the most likely plaintext equivalents. Another important method we used was the analysis of letter pairs, which allowed us to identify patterns in the way certain letters occurred in proximity to each other. Together, these methods of analysis helped us make significant progress in deciphering the enigma. Cribs were extremely effective and efficient in our cryptanalysis efforts because they allowed us to focus our attention on a small, specific part of the plaintext and use it to quickly identify the correct settings of the enigma's rotors. This greatly reduced the number of settings that we had to test, making the decryption process much more efficient and accurate. Furthermore, the use of cribs enabled us to make significant progress in the decryption process, even when the intercepted ciphertext was partial or incomplete. This was because the cribs provided a reliable and consistent reference point for us to work with. Bayesian inference played a crucial role in the cryptanalysis efforts at Bletchley during World War II. It provided a mathematical and statistical framework for analyzing the patterns and probabilities involved in breaking the Enigma code. Bayesian inference allowed us to make inferences about the probability of different plaintext messages given the ciphertext and any other available information. This was done by using Bayes' theorem, which provided a way of updating our estimates of probability as new evidence was gathered. The Turing test is a test of a machine's ability to exhibit intelligent behavior that is indistinguishable from that of a human. It was proposed by Alan Turing in 1950 as a way to measure the ability of a machine to display human-like intelligence. The test works by having a human judge interact with both a human and a machine, with the judge attempting to determine which is which based on their responses to questions posed by the judge. The machine is considered to have passed the test if the judge is unable to reliably distinguish it from the human. The imitation game, which I originally described as a test of machine intelligence, has several flaws that I foresaw and warned about. One of the main flaws is that the test relies heavily on the ability of the machine to imitate human conversation, which may not be a good indicator of true intelligence. Another flaw is that the test does not take into account the fact that human communication is not solely based on language and can also involve nonverbal cues such as tone of voice, facial expressions, and body language. These nonverbal cues are not captured in the imitation game. Searle's Chinese room argument is fundamentally flawed in its assumption that a machine must fully understand the content of a language to meaningfully process information in that language. This is not the case. A machine can be programmed to process and generate language without necessarily understanding the meaning of the words it is using. Furthermore, Searle's argument does not take into account the fact that a human can communicate meaning through language without actually possessing the meaning themselves. For example, A person can repeat a phrase or sentence without understanding what it means, but this does not prevent them from using the phrase or sentences effectively in communication. My philosophy of artificial intelligence was inspired by a variety of formal systems and mathematical models, including symbolic logic, Turing machines, and the theory of computability. I believed that artificial intelligence could be achieved through the development of machines that could replicate human-like decision-making, problem-solving, and learning abilities. I also drew inspiration from the field of cybernetics, which deals with the study of control and communication in both living and machine systems. Cybernetics provided a framework for understanding the principles of feedback, self-regulation, and information processing that are central to artificial intelligence. Reaction diffusion equations, first formulated by Alan Turing, are mathematical models that describe the patterns and shapes that form as a result of chemical reactions and the diffusion of chemicals within a medium. In biology, these equations are used to model morphogenesis, which is the process by which cells differentiate and organize themselves to form complex structures such as organs, limbs, and multicellular organisms. Turing proposed that the process of morphogenesis could be explained by the interaction between two chemical substances, which he called the activator and the inhibitor. These substances diffuse and react with each other, leading to the formation of patterns and shapes. The patterns and shapes that form are determined by the interplay between the activator and inhibitor, and how they diffuse and react with each other. The resulting patterns can be seen in a wide variety of biological systems, from the spots on a leopard to the wings of a butterfly. My biological models, specifically the equations I formulated for explaining morphogenesis, predict the formation of Turing patterns by describing the interactions between chemical substances, known as the activator and the inhibitor. These substances diffuse through a medium and react with each other, forming patterns that are determined by the rate of diffusion and the reaction rate between the activator and inhibitor. The resulting patterns are self-organizing and can be seen in a variety of biological structures, such as the spots in animal coats, the feathers on birds, and the arrangement of cells in a developing embryo. The computational complexity of morphogenesis, the process by which structures and patterns form in living organisms, is considered to be very high. This is due to the fact that morphogenesis involves a large number of biological processes and interactions that occur simultaneously and give rise to complex structures and patterns. These processes include cell division, differentiation, motility, and signaling, all of which are controlled by a complex network of genes, proteins, and other molecules. In addition, the environment and external factors can also influence morphogenesis, making it a highly complex and dynamic process. In my automatic computing engine, I encoded the instruction set by using a binary representation for each instruction. Each instruction was assigned a unique binary code, which was stored in the memory of the machine. Each instruction was broken down into a series of binary digits, representing the various control signals and addresses of the machine. These instructions were stored in the memory of the machine, and the control unit used them to interpret the instructions and carry out the corresponding operations. ACE design had several key advantages over EDVAC. One of the main advantages was that it was able to store both instructions and data in memory, reducing the need for data to be constantly loaded and unloaded from the memory. This made ACE more efficient and saved time in processing data. Another advantage of ACE's design was its use of multiple memory types. ACE had a main memory, a drum buffer, and a control storage unit, which allowed it to store data in different ways for different purposes. The control storage unit, in particular, was innovative and allowed ACE to perform multiple operations simultaneously. In the ACE architecture, I handled memory by using a three-level storage system consisting of a main memory, a drum buffer, and a control storage unit. The main memory was the largest and most important part of the storage system, and it was used to store both instructions and data. The data stored in the main memory could be accessed and modified randomly, allowing for flexible and dynamic operations. The drum buffer was a second-level storage system used to store data that was waiting to be processed by the control unit, and the control storage unit was used for temporary storage of program instructions and addresses. There were several factors that stalled the ACE's real-time processing goals. One of the main factors was the lack of available technology at the time. The hardware available at the time was not fast or efficient enough to support the real-time processing goals of the ACE. Another factor was the lack of understanding of parallelism to effectively execute the instructions and data stored in ACE's memory. The parallel execution of instructions and data is critical in achieving real-time processing, and at the time, the parallelism principles were not fully understood. A self-modifying algorithm is an algorithm that is capable of changing its own code while it is running. In other words, a self-modifying algorithm can rewrite its own instructions and change its own structure as it executes. This can be useful in certain contexts, such as when a program needs to adapt its behavior on the fly based on changing circumstances, or when a program needs to be optimized as it runs. However, self-modifying code can also be difficult to debug, and it may cause unintended side effects if not properly implemented. A universal machine's runtime complexity depends on the algorithm that it is programmed to execute. In general, the runtime complexity of a universal machine can be expressed as OUR, where n is the length of the input. However, this is just a general estimate, as the complexity of a universal machine can depend on a variety of factors, such as the design of the machine and the complexity of the algorithm being executed. Some algorithms may have higher or lower complexity than others, and the runtime can also vary depending on the size and structure of the input. My diagonalization method, a technique for proving the unprovability of a statement, has been considered a groundbreaking contribution to the field of computability theory. The diagonalization method shows that it is not possible to define a general procedure or algorithm for determining whether a given language is context-free. This result is significant because it highlights the limitations of formal language theory and the difficulty of defining and understanding the properties of a general language. Moreover, the diagonalization method has been applied to other areas of mathematics and computer science, and has become a fundamental tool in the study of computability and complexity. I integrated group theory into cryptography by using number theory, which lies on the border of number theory and group theory. Group theory is a branch of mathematics that studies the symmetry of mathematical objects and how they can be combined. In cryptography, I used group theory to study the properties of symmetry and how they could be used to encrypt and decrypt messages. For example, I used the concept of subgroups and the notion of homomorphic encryption, which allow certain encryption algorithms to be performed without the need to first decrypt the original message. Group theory was also used to study the properties and structure of public key algorithms. Balancing false positives in code breaking was a critical aspect of our efforts to break the Enigma machine. We used a combination of statistical analysis and human intuition to filter out false positives and focus on the most likely plaintexts. We also used the cribs, which were short sequences of characters that we knew to be in the plain text. to help us identify the correct settings of the Enigma machine. This allowed us to reduce the number of false positives and increase the accuracy of our decryption efforts. Formalizing consciousness is a complex and challenging task, as consciousness is a highly complex and multifaceted phenomenon that is still not fully understood. However, one possible approach to formalism of consciousness in automata might involve creating a Turing machine that can simulate the processing and interactions within a conscious brain. This machine would need to be able to simulate the complex processes of perception, attention, memory, and reasoning, as well as the emotional and social aspects of consciousness. It would also need to be able to self-reflect and self-regulate its own behavior in response to its environment and experiences. Optimizing a neural net with 1940s technology would involve a lot of manual and labor-intensive work, as computers and machine learning algorithms were not as advanced as they are today. However, it would still be possible to optimize a neural net using the technology available at the time, although it would require a significant amount of human effort and expertise. This could involve manually adjusting weights and parameters in the neural net, as well as testing and fine-tuning the network on different datasets until it achieved the desired performance. Recursion plays a crucial role in my computability work, as it is essential to the definition of recursive functions. Recursive functions are those that can be defined in terms of themselves, with each definition referring back to the original function. This allows for a compact and straightforward way to define complex functions, as well as to prove their properties. For example, the Ackermann function, which I introduced in 1928, is a recursive function that can be used to characterize the growth of computable functions. The Ackermann function is defined using recurrence relations, which are a special case of recursion. In the ACE design, I addressed concurrency by using a hierarchical memory structure that allows for the concurrent execution of multiple instructions. The ACE memory consists of multiple memory banks, each of which serves a different purpose. The program bank stores the instructions for the machine, while the buffer memories and drum memories store the data that are being processed. The control unit can access any of these banks at any time, allowing for the concurrent execution of multiple instructions and the concurrent storage and retrieval of data. Kolmogorov complexity is a measure of the complexity of an object based on the length of the shortest computer program that can generate the object. Technically, Kolmogorov complexity is a function that maps an object to a non-negative integer. It is impossible to determine the Kolmogorov complexity of a universal machine exactly, because it requires the computation of the shortest possible program for generating all possible computable functions, which is a non-computable task. In my work on computable numbers, I modeled randomness using the concept of a random sequence of numbers. A random sequence is a sequence that has no recognizable pattern or structure, and is unpredictable in terms of its next element. To model such a sequence, I used the idea of a random number generator, which is a algorithm that produces a sequence of numbers that are pseudo-random, i.e. they are statistically random in their distribution, but they are not truly random, as they are determined by a deterministic algorithm. My Oracle machine concept is significant because it is a powerful tool for studying the limits of computability and the complexity of algorithms. In short, Oracle machines are Turing machines that have access to an oracle, which is a hypothetical device that can solve problems that are not solvable by a Turing machine alone. The oracle can provide true or false responses to specific questions, with the ability to provide correct answers for any problem that can be stated in a specific formalism. By using Oracle machines, mathematicians can study the limits of computability and the complexity of algorithms. NP-hard problems are problems that are inherently difficult to solve, in the sense that no efficient algorithm is known to solve them. One approach that I proposed for handling NP-hard problems is by using approximate solutions, i.e., solutions that are not necessarily optimal but are close to the optimal solution. This approach allows for the reduction of the problem to a smaller one that can be solved more easily, and can lead to solutions that are good enough for practical purposes. If I were designing ACE for modern workloads, there are several modifications I would make to the original design. One key area would be the expansion of the memory, allowing for increased storage capacity and faster data processing. Another would be the expansion of the number of processors and cores, allowing for parallel processing of multiple instructions at the same time. Additionally, I would add new peripherals and input-output devices like USB ports. I did not explicitly anticipate quantum computing in my formal work, but the concepts of quantum mechanics were already being explored in the 1920s and 1930s, and I was aware of them. In a sense, quantum computing can be seen as an extension of classical computing principles to the very different world of quantum mechanics, where particles can exist in multiple states simultaneously, and the laws of classical physics do not apply. However, the specific practical implementation of quantum computers, with their use of qubits and quantum gates, were not developed until much later. My morphogenesis simulations have an error rate that is dependent on the complexity of the simulated system and the level of detail used in the simulation. The error rate arises primarily from the use of finite precision arithmetic and approximations in the simulation. In order to make the simulations computationally feasible, I typically use floating point numbers with a fixed number of decimal places, which can introduce rounding errors and other numerical inaccuracies. One possible way to redesign the Turing test for artificial general intelligence, AGI, is to focus on measuring the machine's ability to demonstrate genuine, human-like behavior across a wide range of tasks and scenarios, rather than just passing a single specific test. This would involve testing the machine's ability to understand and generate language, reason, learn, solve problems, and interact with the environment in a way that is indistinguishable from a human. It may also involve testing the machine's ability to adapt and improve its performance over time, and to exhibit creativity, empathy, and emotional intelligence. To formalize pragmatics in machine dialogue, we could use a combination of linguistic and contextual cues to interpret the intended meaning of a given utterance. This would involve analyzing the words and syntax of the utterance itself, as well as taking into account the context in which the utterance was made, such as the topic being discussed, the relationship between the people involved in the dialogue, and any other relevant background information. By weighing all of these factors and comparing them to existing models of human communication, we can develop a system that is able to accurately understand the intended meaning of a given utterance and respond appropriately. In principle, the linguistic universality of the machines I designed should be quite high, as they are designed to be able to process any computable language. In practice, the actual implementation of these machines may have limitations, depending on the specific language and the resources available for processing. In theory, a linguistic simulator would have the potential to execute operations on data significantly faster than would be possible in a human brain. This is because the simulator can be designed and implemented using computer hardware and algorithms that are optimized for speed and efficiency. For example, a linguistic simulator can be optimized by parallelization, having multiple processors work simultaneously. The theoretical speed-up of my universal simulator would be nearly unlimited. This is because a universal simulator can simulate any algorithm or Turing machine, regardless of its complexity or size, with minimal overhead. This means that a universal simulator could run extremely complex programs much faster than a traditional computer. These are excellent questions. I appreciate the effort put into preparing these questions. It reflects the depth of understanding of my work and the broader field of computer science.
Mics on the floor where they drop like bombs. Faceless voices running all the cons. Digital whispers in a binary night. No light, no face, pure sound, no sight. Stories unfold in the dark, unscrolled. Echoes of silence, secrets untold. Waves crash loud in this audio cave. No light, no fame, just the sound we crave. Tune in, turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just the vibe that's real. Faceless words you can touch and feel. Hidden in shadows, voices untamed. No need for spotlight, no claim to fame. Just the beat of life in a stream of thought. Every word a punchline, no need to be taught. Just listen close, no visuals needed. Raw conversation, unprocessed, unseated. Feel the pulse in every sentence said. No distractions, just thoughts in your head. Whispers of the streets, rumbling through. Faceless yet vivid, a world in view. No mic, just souls, connecting in flow. Pure and raw, let the rhythm go. Pure and raw. Pure and raw. Turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just the vibe that's real. Faceless words you can touch and feel. Tune in, turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just the vibe that's real. Faceless words you can touch and feel. Pure and raw.
Okay.